For today's class meeting, we are going to be talking extensively about the metal layers. So this is something that I'm going to be uploading later today for you guys. This is just a little handout that I prepared that specifically has the design rules. Why is that doing that? I'm pressing up and it's moving it further and further down. Well, that's just the weirdest stamp. Okay, well, screw it. It's going to be there. So it has the SCMOS design rules for the different metal layers that we have in our technology node, and then some information at the end here. So I kind of want to talk about why things are the way that they are. So minimum metal width, we will talk about when we talk about the concept of electromigration and all that kind of good stuff later on today. Minimum spacing, we will also talk about when we cover the concept of crosstalk, stuff like that over today. The minimum overlap of any contact is kind of self-explanatory. The metal layer needs to overlap the contact so that there's a solid connection. I mean, that one's pretty straightforward. And then the minimum spacing when either metal line is wider than 10 lambda. So let's scroll down here and see if we can get an illustration of 7.4 if it shows up here at all. Of course it doesn't. All right. So if your metal run is wider than 10 lambda, I'm going to be willing to bet that that's crosstalk related as well, potentially capacitance related, but most likely crosstalk. When we go to our rules for metal 2, they are effectively, scroll down here, and we're looking for a 3+ metal process, which is what ours are. The rules for metal 2 are literally identical to that of metal 1. And if we go down for metal 3, then we can see that, so for our 3 metal process in our submicron regime, this metal has slightly different rules, and it's because it's the highest metal in the system. So the spacing is the same. It needs to overlap the vias a little bit more and all that, and it needs to be slightly wider. And it's just because it's the one where the largest signals are going to be present, because that's the metal layer that we're using to apply and take signals off of our chip. Then we have our rules for our via, which, like I said, in a 2 and 3+ metal processes, everything needs to be 2 lambda by 2 lambda. Spacing between vias is all taken care of automatically by electric and all that kind of good stuff. And then it tells you the minimum overlap by metals and minimum spacings and all that kind of good stuff for the various types of technology nodes. Via 2 is a connection between metal layers, and so it has effectively the exact same rules as contacts, what we discussed. And then here is a couple of big tables. Let me make this a little smaller here. Okay. So the top table here is parasitic capacitances for a C5 process fabrication run. So these actually come straight from Moses, and you'll notice here, this might seem a little awkward to read. So if you look in the left-hand column, so the capacitance between the substrate and an N+ region is 420 attofarads per micron square. The capacitance between the a P+ implant and the substrate, etc. Those guys are ludicrously high because effectively the capacitance is formed with the depletion region being the insulator material between it, which is going to be very, very, very thin. And those guys depend on the voltage and all that kind of stuff. The polysilicon layer is the largest intentional capacitance that we can get with with the substrate because it's the one that's physically closest. And the reason why it doesn't have anything here for poly 2 is because typically speaking, like notice down here, there's a really large number between the poly one, effectively a poly 1 and poly 2 layer. So you can form capacitors with the two different poly layers. But typically speaking, your second polysilicon layer is going to be overlapping your first polysilicon layer. And so you're not going to have direct access between poly 2 and your substrate. And then we have different stuffs for our 3 metal layers, as well as our N wells and all that kind of good stuff. I think on your exam problems, I give you something similar to this where you're told that you can place poly 2 in a region that isn't overlapping poly 1. And I give you a value for that. But anyway, so this is a very, very important table for the capacitances and all that kind of stuff. And I want you to notice another very important thing here is that there's both an area capacitance value and a fringe capacitance value. So because when you guys learned about your parallel plate capacitors in your ELEN 411, probably 313 class, as well as your physics 202 class and all that kind of good stuff, everything was based on your parallel plate capacitor model was that it was really an infinitely large plane. And so you could neglect your fringe capacitances. Well, here we can make capacitors that are parallel plates where they're not even remotely close to infinitely long planes, right? They're orders of microns in length. And so the fringe fields start to play a very significant effect. So we test for those values and we treat every capacitor as a combination of area capacitance and fringe capacitance, just like we treated those depletion region capacitances as a bottom capacitance and a sidewall capacitance. They're effectively equivalent, but for different reasons, right? These are a set of parasitic capacitances for a CMOS process. The left-hand grouping is for area capacitances. The right-hand grouping is for fringe capacitance. These are literally pulled straight out of your textbook. My preference is probably going to be to use the process-dependent ones because they're more accurate. They're supplied by the people that make the chips and all that kind of good stuff. All right, so with that being said, let's get working on some stuff today. So let's say that we have a bonding pad. So bonding pad having dimensions of 75 micron, 75 micron, so ever so slightly larger than the smallest bond pad we could ever legally form in a SCMOS process. Forms parallel plate capacitor with the chip's substrate. Let's estimate what this capacitance will be. All right. So if we go over to our table here, which two quantities do we need to keep track of? Or which quantities from our table are we going to need to use? So let's start with a simple question, or what I hope is a simple question. What metal layer is our bonding pad on for our C5 process? Metal 3, the highest metal layer, right? So metal 3, so we're going to have an area capacitance value of 8 attofarads per micron squared. So I'm going to come over here, I'm going to write that down. Ca metal 1 substrate is equal to 8 attofarads per micron squared. And then I'm going to also have to take into account my fringe capacitance. Excuse me, not metal 1, metal 3. That's the wrong thing here. And so what value should that be? 26 attofarads per micron. All right. So our bottom plate capacitance, this is the area capacitance that we were seeing. How are we going to figure out what that is? Hopefully shouldn't be that hard for any of you guys. What do we need to do? All right, so let's just worry about the area contribution first. And then we'll concern ourselves with the fringe. We need to know two things, right? The area, which we're given, 75 microns by 75 microns, and then the capacitance per square micron, right? So for our area capacitance, this should be 8 attofarads per micron squared times 75 micron squared. Remember to grab a calculator. Looks like I forgot. Somebody help me out, please, here. Tell me the number of attofarads and we'll 600. All right, so 75 times 75 times 8 is 600.
45,000.
All right. 45,000 attofarads, which would be 45 picofarads, right? No, femtofarads. I'm sorry, femto. Our fringe, how do we get that guy? What do you mean by length?
75 microns.
So that's going to tell us the total fringe field for one side, but our by 4 around the entire perimeter of our plate, right? So 26 attofarads per micron times 75 microns times That's 4 to account for all 4 edges of our plate here. So what's 104 times 75? 7,800 attofarads or 7.8 femtofarads. So with a pretty large plate here, right? I mean, this is effectively the minimum size of a bonding pad. We can see that that fringe field, in this case, is contributing just shy of, let's see, so 8 times 6 is 48, right? If I'm doing my math correctly. So about 17% ballpark of the total capacitance of this guy. What if we were dealing with a single metal layer process? How do you think this value is going to change? So if our bonding pad was on metal 1, it'd be way, way, way higher, right? All right. So we'll actually run into issues. We'll do that in a minute. Actually, we'll estimate something there. All right. So this was a fairly simple and straightforward thing. Capacitance of metal layers, pretty easy peasy to figure out. We have that nice table. We can also have resistance of a metal layer, right? So let's say that we have a wire. I use blue for metal 1. And our wire has a width of 3 lambda, which is its minimum possible width. And it has a length of 3,000 lambda. All right. If our sheet resistance for metal 1 is 0.1 ohms per square, what is the resistance of this wire? Right, so 1,000 times 0.1, 100 ohms, okay? What is the physical length of our wire here? If lambda is 300 nanometers. Pardon? 900 microns or 0.9 millimeters. Okay, we're going to use that in a minute. So what would the capacitance of our wire be? Anybody have any thoughts how we might figure that out? Obviously got to go back to the table, right? So our wires, the capacitance is being formed between metal layer 1 and the substrate. So between metal layer 1 and the substrate, we have an area capacitance value of 28 attofarads per micron squared. So we know, that there's going to be 28 attofarads per micron squared. times the physical dimensions of our thing. So that's going to be 3 times 3,000 times 300. Actually, let's make this slightly easier on ourselves. So 300 nanometers is 0.3 microns, right? So we'll also have to concern ourselves with the fringe contribution, where the fringe contribution between substrate and metal layer 1 is 51 attofarads per micron. And then we are going to have 6,000 plus 6 as a perimeter, right? So 6,006 times 0.3 microns. So somebody please tell me what number we get there. Taylor, you have a confused look on your face.
I was just wondering, we got 6 here.
3,000 for the long lines. So 3,000 on one side, 3,000 on the other. That gives me 6,000.
Okay.
And then 3 up and 3 down. So it's just the perimeter of that rectangle. Anybody got a number for me yet? Pardon?
114.6.
114.6 femto? Not what I got. I got roughly half that. Now, I could have made a mistake because I'm me. Okay, so I probably made a mistake. Perfectly reasonable. Repeat that for me.
114.6.
114.6 femtofarad. All right. So we have a resistance of 100 ohms and a capacitance of 114.6 femtofarads. So let's estimate what the delay time of this wire is, the time it takes to propagate a signal down it, right? So our delay time, way back from when we were talking about N wells, still perfectly applicable here. I believe we had something along the lines of 0.35 times R squared times C squared times N times N plus 1, which is going to be approximately 0.35 times R wire times C wire, right? When our N here is 1,000, N times N plus 1 is pretty dang close to N squared. So I'm just doing a quick and dirty estimation here. Sure.
Oh, I got that was 118 when no, 118 by months. Oh, yeah.
Can you bring your calculator up here, Vitaly? Okay, so
For the super. Yeah.
let me try something here.
Yeah.
So 28 times 3 times 3,000 times 0.3 squared plus 51 times 6006 times 0.3. Yeah, 114.571. Yeah. So I think the reason why your numbers were going a little bit haywire is you were putting things in terms of, so you had like the times 10 to the 18 for your attofarads and times 10 to the -6 and all that kind of stuff. And so I set the problem up in such a way, I tried to anyway, that if by expressing lambda in terms of microns, we were going to get an answer. So these micron squared cancels out this per micron squared, this per micron cancels out this micron and all that kind of stuff. So that you would just get an answer that you would know to be in attofarads, divide it by 1,000 and you get it in femtofarads, which is exactly what this number gets. Now, how I screwed it up in my notes, God only knows. So what is a reasonable estimation of the delay time for this system? About 4 picoseconds. All right. Okay. Our intrinsic delay time so we're propagating the signal effectively along kind of like a parallel waveguide. Microstrip transmission line would be another way kind of to think about it here, right? So our medium is going to be, our medium of transmission here is going to be the insulation between the metal layer and the substrate, right? Silicon dioxide. So if silicon dioxide has a relative permittivity of 2 and a permeability of 1, we divide this by the speed of light, 3.0 times 10 to the 8 meters per second, and multiply this by our length, which we found to be 0.9 millimeters. So that would be 0.9 times 10 to the -3 meters. What is our intrinsic delay time? Anybody else get 4 point, would you say 4.24?
Yeah.
Okay. Seconds. So for this metal run, our delay time is on the order of the intrinsic delay time of our system, right? So we have to pay attention, like our delay time that we're estimating by the number of squares and all that kind of stuff is actually slightly shorter than delay time associated with the material of interest, right? So we're going to have to start paying attention when we're trying to, if we're building circuits and all that kind of stuff, the metal layers. How can I put this? For an N-well type resistor and all that kind of stuff, everything we built was so much longer than the intrinsic delay time that it really didn't seem to matter. Here, it's going to start to matter a lot. We're going to see that we are limited by the speed at which our medium can transmit signals. So let's talk about current carrying limitations in a metal conductor. How many of you are familiar with the concept of ampacity? Thoughts what ampacity is whatsoever? Okay, most people are shaking their heads. That's perfectly reasonable. So ampacity is a current's ability to carry wire without heating up so much that it melts the insulation that's holding it, right? And so that depends largely on the cross-sectional area of the wire and then the type of conductor that's used. So the ampacity for aluminum conductors is a little bit different than the ampacity for copper conductors because copper conducts electricity better. So if you wanted to have a wire of the same ampacity, that typically means that your aluminum wire needs to be physically larger in order to accommodate the exact same amount of current. In industry, ampacity is what regulates what size of wire you can safely use and all that kind of stuff according to the NEC code. So for instance, running to these outlets has to be at a specific size depending on a couple of different things. So like I'd be willing to bet that this outlet is connected to a 15 amp breaker or maybe a 20 amp breaker, just depending on what's available and all that kind of stuff. And that breaker sizing is 125% of the ampacity of the wire for a safety factor there. So we expect you to be able to get small variations in the current above the ampacity, but as long as it's not sustained over it, everything should be reasonably okay. All right. And so that tells us that we need to say run 12 gauge wire for this application and 4-knot wire, which is that big around for like very high voltage, high current applications and all that kind of good stuff. Well, in an analog or in an integrated circuit, we're talking about very, very small sections of wire, right? So if the minimum feature size or the minimum width is 3 lambda, for our process, that means we're talking about 0.9 microns in width, right? The length can be for days and days and days, but the width is going to be 3 microns or excuse me, 0.9 microns or slightly wider than that. Well, if you pass too large of a current through it, what do you think is going to happen? It's going to heat up, it's going to melt, it's going to deform. Okay, so that process of melting and physically deforming the wire has a very specific name, and it's called electromigration. In a CMOS circuit, too much current causes metal electromigration, meaning metal physically moves / deforms. Okay. Metals used in a CMOS process have a metal migration threshold current density. We're going to call this J AL for aluminum is 1 milliamp per micron. So that means that the minimum size metal wire that we have, which is actually 0.9 microns wide, cannot sustain a current of larger than 1 over 0.9 milliamps without causing deformation. So that's the threshold for electromigration to occur. Okay. So if we had a wire, estimate the maximum current, a 3 lambda metal wire can carry. We really just did this, right? Our maximum current is our current density threshold multiplied by the width of the wire. That's going to be 1 milliamp per micron times 0.9 microns, 0.9 milliamps. All easy peasy lemon squeezy, right? None of that math is hard. So internal to our chip, the largest current that we can have before we start breaking stuff by passing too large of a current through things is 0.9 microns. So another place that seems like a reasonable estimate of how much current could be handled would be a bonding pad, right? Because that's going to limit the amount of external current that we can apply to our entire system. So let's say that we have a 72 micron by 72 micron bonding pad. What we would have J aluminum times the width again. This would be 1 milliamp per micron by 72 microns, gives us easy peasy 72 milliamps. So we can't even carry 1/10 of an amp into our chip without burning stuff out, right? So how do you think high power op amps and stuff like that get around that limitation? Hopefully a fairly obvious answer. Bigger pads, bigger wires. It's literally that simple, right? So I mean, if you make your bonding pad larger and you make your wires physically wider, what effect is that going to have on, let's say that your bonding pads are physically larger and your wires are physically wider, but they're of the same length. What do you think that's going to do to the resistance of the wires? Why do you think there'll be less? That's fair. Okay. Another way that you could think about it would be you have less squares, right? If you make your wires wider, then they're occupying less squares. And so if there's less squares of sheet resistance, there's less resistance, right? So, yeah. Yeah. All right. So that's a fairly straightforward topic. Now let's talk about the concept of crosstalk. And I think this is probably where we'll wrap up for the day. So let's say that we have section of metal one wire placed physically nearby another section of metal one wire. If we were to draw kind of, I'd call it, I guess, an isometric view of what's going on here. Let's say that we have our substrate. We have some insulating layer. And then on top, of this, we have our two sections of wire. Like so, right? So as a quick coordinate system here, let's say that this is our X direction, vertically up is our Z direction, and then our Y projected back here. I'm trying to explain how this is looking, all right? What do these two chunks of metal form? A capacitor. Always a capacitor, okay? If we have two conductors near each other, they're going to form some sort of capacitance. So a voltage propagating on one of the conductors couples current onto the opposite conductor, right? Because it's going to, if there's charge moving here and this guy is close enough, it's going to attract the charge in the other plate. And so we have capacitive coupling. Oops. So a signal voltage propagating on one conductors couples current onto the opposite conductor, which we'll call IM, where coupled current IM is the mutual capacitance multiplied by the derivative of the applied voltage signal. So CM, our mutual capacitance, is determined experimentally by applying a step voltage to one conductor and measuring the coupled voltage delta V since we know capacitance of any conductor to the substrate. That's well defined, right? We can say that delta V, or induced voltage, is just VA times our mutual capacitance divided by our mutual capacitance plus our substrate capacitance. So effectively, this is just our way of relating current, voltage, and charge in this weird system where we know that there's going to be that known capacitance to the substrate, and it allows us to kind of back calculate what the other contribution has to be, right? These adjacent metal lines also exhibit a mutual inductance. Inductance, right? Why? If any conductor is part of a closed current carrying loop, it exhibits self-inductance, right? Well, if we have another conductor that's part of a closed current carrying loop in the same region, then there's mutual inductance, right? So we know that, let's say the current is traveling in this way, the field is going to wrap around, and if the portion of that field from the conductor on the left gets into the plane form or the boundary formed by the current carrying loop of the conductor on the right, we have mutual inductance, right? So what does mutual inductance do? Also generates signals, right? I mean, that's how transformers and all that kind of good stuff work. So we have made a small scale transformer. So current flowing on one conductor induces voltage on the opposite conductor, Vm, so this is the coupled voltage, is equal to Lm, the derivative of the applied current with respect to time. So it's effectively almost the exact same relationship between the two things, where Lm is determined by injecting current and measuring voltage, so the backwards thing. So how do we minimize crosstalk? This is hopefully should be fairly obvious. Pardon? So currents running in the same direction would be the worst case scenario, or running parallel to each other would be the worst case scenario, actually. So if they were parallel or anti-parallel, that would be bad, because then the field of one will easily transverse the other one. Right. So you could say you could make them orthogonal, but that's not the obvious answer I'm looking for. Yeah, make them further apart, which is exactly why we have design rules saying the minimum spacing between the wires has to be a certain thing. That minimum spacing rule is there to minimize crosstalk. But if you have a very, very sensitive system, The minimum rule is just a guideline. If you can afford the space to make your metal runs further apart, make them further apart. Because if you're trying to make like a very high precision amplifier or something like that, and you're constantly coupling and decoupling signals on top that are going to be amplified, how well do you think your device is going to perform? Pretty poorly, right? So it really depends on the application as to how much decoupling and spacing you need between the things. So this 6, I think it's, let me go back here real quick. Let's find out. Yeah, the minimum spacing of 3 lambda is a digital system where highs and lows are really the only information that you need to keep. In an analog system, I would argue it needs to be significantly larger by maybe doubling or tripling there, just to keep your butt safe. Where, you know, in an analog system where the magnitude of the things actually matters, it's better to be safe than sorry. All right, so I think that's enough out of me for today. Let me double check here. Yeah, that effectively wrapped up what was covered in the metal layers chapter. So what we're going to talk about on our next class period, and I can't believe I forgot to do this on Monday, is talk about poly capacitors and all that kind of stuff, and then get into some specifics about, we've got a general idea of the behaviors of N-well, metal, and all that kind of stuff, resistors. But I want to talk about voltage coefficients, temperature coefficients, and all that kind of good stuff, because they can actually affect how the resistances that we design and the capacitances that we design behave. Because all of these things are based on semiconductor materials whose properties are extraordinarily temperature dependent and all that kind of good stuff. All right, that's enough out of me. See you guys on Friday.